Chapter 21, Plate Tectonics and the Earth's Interior. Section 21.1, Seismic Waves. So at this point, you've probably all heard of earthquakes, right? An earthquake is just when the ground shakes due to movements underneath the ground. We're going to talk in a few sections more specifically about earthquakes in general, but you just have to know that they exist to understand the rest of this section. So when you have an earthquake that occurs, those earthquakes cause the ground to vibrate, to shake, and these generate what are called seismic waves. Seismic waves are just waves of energy that travel through the earth due to earthquakes. The speed and the path that a seismic wave takes is what gives us an insight into what the inside of the earth looks like. We can't dig a hole to the center of the earth. You can't go down into the center of the earth to figure out what's there. So we need another way to look. In fact, the deepest you could dig would not even get you through the top part of this continental crust here. You couldn't even get to the mantle, let alone dig all the way through the earth. So we need to use seismic waves to understand what the inside of the earth looks like. By doing that, over the past 100 years or so, we've determined that the earth is split into 4 different layers. The crust on the outside, and then below that the mantle, which makes up most of the earth, and then the outer core and the inner core. In the next section, we'll talk about these in detail. So the speed of a seismic wave is determined by the material that it travels through, the medium that it travels through. So if we know how fast those waves are traveling, we can figure out what stuff it's traveling through. So we can figure out what the inside of the earth looks like. When we have seismic waves, we measure those things with a device called a seismograph. These are the little paper things you see in movies that have the needle that moves up and down. And the earth starts shaking and the needle starts moving faster and faster. That's a seismograph. Seismographs would be buried all over the place, especially near places like fault lines and things like that. But they're also buried and put in places where you wouldn't have fault lines. And what happens is when you have an earthquake register somewhere in the earth, the bigger the earthquake, the more it'll travel through the earth. But regardless of how big the earthquake is, in general, you can still track it through the seismic waves in the earth just by measuring the small movements. And by having seismographs placed along the Earth's surface at known distances, you know how long it takes for those waves to go through the Earth to get to that point. And from that, you can figure out what is going on, what kind of stuff that wave is traveling through. So there are 2 different types of seismic waves that we use to determine the interior aspects of the Earth. They're what are known as body waves, which travel through the Earth's interior, and then there are surface waves, which travel along the surface. In terms of body waves, we classify those into 2 groups. The first are what are known as primary waves or P waves. Okay, these are what are known as longitudinal waves, which means that the wave itself vibrates parallel to the direction that it travels. Sound waves are longitudinal waves. When you speak, you vibrate the air in front of your mouth, and that vibration travels through the air. You can also observe a longitudinal wave by taking something like a slinky and spreading it out and then compressing some of the slinky and releasing it. And what will happen is that compression from the slinky will travel through the slinky and back. And that's a longitudinal wave. Primary waves, because they're longitudinal waves, travel very easily through solids and through liquids. So they can travel through any material. And so we can measure the times that those primary waves travel through solid materials or liquid materials. And so if you know, say, how fast that primary wave traveled through the mantle, you could figure out basically the density of the mantle or what it's made out of. Secondary waves, which are sometimes called S waves, are what are known as transverse waves. And transverse waves vibrate perpendicular to the direction that they travel. So they vibrate up and down as the wave moves forward. This is what you think of when you think of like water waves. Water waves are transverse waves. You see the wave move up and down, or the water move up and down, but the wave itself moves forward. Secondary waves are the second to register, hence the name, and they cannot travel through fluids, so they can't travel through liquids. By knowing this, by knowing that P waves can travel through everything, and secondary waves can't travel through liquids, we can figure out which part of the Earth's are liquid, or which part of Earth's internal layers are liquid, and which parts are solid. So a P wave could travel through all the solids and liquids, and S waves couldn't. So for example, we know that the inner core of the Earth is solid, the outer core of the Earth is molten metal. S waves could not travel through the outer core to get to the inner core. If they hit the outer core, they would just stop. And so this allows us to know, A, where the outer core is, but it also tells us that there's no solids there, that it's liquid. The other thing we can determine is where the boundaries are between these different layers. So when waves change the medium they travel through, they can be bent. This happens with light when you're looking at a straw in a glass, right? When you look at a straw sitting in a glass of water, if you look where the line of the water is, where the straw appears to come out of the water and where it appears to be in the water looks different. The other way of kind of envisioning this is fill your bathtub up with water, drop a penny to the bottom, then take your finger and try to put your finger down directly onto the penny. The penny will appear to be in a slightly different place than where it actually is. And it's because you're observing the light as it passes through the water. This is the same thing that's happening inside the Earth. When those P waves and S waves change mediums, when they go from the crust to the mantle or from the mantle to the core, the waves are bent in a particular way. And the way those waves are bent identifies where those boundaries are. There's obviously a lot more to it that I'm leaving out in terms of understanding how you could actually calculate that. But this is the way that it's done. It's done by just measuring these waves and determining where they change. So that would tell you where the boundaries are and what substances they go through and which ones they don't. And so that tells you where the solids and the liquids are. So body waves are really what we use to measure the internal structure of the Earth. The other parts that come about, the other seismic waves that come about from earthquakes are what are known as surface waves. And these are the ones that just have an impact on humans, as we are the ones who live on the surface. And there are two different types of surface waves as well, Rayleigh waves and love waves. Rayleigh waves are the ones that are the rolling action that you visually witness a lot when you see earthquakes, and then love waves are a back and forth motion of the ground. These surface waves are by far the slowest of all of the seismic waves.